So I'm going to start by roughly giving you an idea of what type of games we play when we say that we are studying special values of L functions. So what does that mean? Well, the game is like this. So I give you an object of arithmetic geometric nature, and this object is most of the time a scheme of some sort over a global field that is either a number field or a function field over a finite field. And then to this object of arithmetic geometric nature, so by the way, if you really have a craving for the utmost level of generality, you can replace the scheme by a motive. You will hear the word motive in my talk today several times. I'll never define a motive here, okay? But you can play the game I am going to describe with motives rather than schemes over global fields. So I give you this object of arithmetic geometric nature, which is a scheme in general over a global field. And to this object, you can associate two types of invariants in general, okay? One kind of invariance that you can associate is the invariance of arithmetic or algebraic geometric nature, okay? Some sort of cohomology groups, for example, motivic cohomology, again, if you want to shoot for the stars here. There is another kind, and those are the analytic invariants. And how do those come about? Well, to an object of this type, you can associate an L function or a family of L functions, which are objects of analytic nature, and then you evaluate these L functions or their derivatives at various points on the real axis. Those values are the so-called special values of the L functions, and they are analytic invariants. And once you have these two classes of invariants, what you would like to do is establish a link, build a bridge between the arithmetic side of the story and the analytic side of the story. That's what it means to study special values of L functions. Okay? You know, today I'm going to talk about a very general conjecture in the world of special values of L functions. And this conjecture is the so-called equivariant Tamagawa number conjecture for motives with coefficients. This conjecture is due to Burns and Flach. I mean, its most general setting is due to Burns and Flach, but these two people built upon work of many other people that worked on this type of stuff in the 80s and 90s. Among them, I should mention Bloch, Kato, Perrin-Riou, Fontaine, and so forth. However, I should warn you that I am only going to be dealing with the equivariant Tamagawa number conjecture in its simplest of cases. Actually, the scheme that I'm going to be referring to most of the time is probably the simplest scheme that showed up in Henri Darmon's talk this morning, and that is the scheme GM. And I'll be interested in its rational points with coordinates in the ring of S integers of a global field, either a number field or a function field in characteristic P. And you know that GM evaluated against the S integers is finitely generated, so GM is a group scheme, so GM evaluated in the S integers is going to be a group, and this group is finitely generated via Dirichlet's theorem. So the arithmetic seems to be quite simple, and the geometry is even simpler. So GM has a very simple geometry. But as you will see, the arithmetic behind this problem is not as simple as it might seem. Because sometimes you can endow this ring of S integers with group action, okay? And the group might act on the OS points on of your scheme. So GM of OS might be a Z bracket G module whose structure you want to understand. Okay? So you know that it's finitely generated over Z. It will be finitely generated over Z bracket G, where G is this group. But understanding its Z bracket G module structure might be very difficult. So in fact, the arithmetic behind this very simple geometric situation, it's extremely complicated, as you will see. And the point I want to make today is that as complicated as it might be, this arithmetic, the arithmetic can be captured by the associated L functions. So all the arithmetic information that you are looking for is hiding somewhere in the analytic world. And what we're trying to do when we're saying we're studying special values of L functions is unlock this arithmetic information by simply building a bridge between the analytic world and the arithmetic world. That's what's going to happen here. Okay, so let me set some notations here. So by the way, for those of you who are interested in copies of these transparencies, I suppose we can arrange with the organizers so that copies can be made. So here is the general notation. So capital K over little k is going to denote an abelian extension of global fields of Galois group G. So G is abelian and it's finite. These are not necessarily number fields. They can be characteristic P global fields. S and T are finite sets of primes in the bottom field, little k, and Sk and Tk are the primes in capital K sitting above primes in S and T, respectively. And now I want S and T to satisfy certain properties. So I want S to be non-empty, and I want it to contain at least all the infinite, that is the Archimedean primes, and the primes which ramify in this extension, and possibly other primes. And I want T to be large enough so that there are no non-trivial roots of unity in the top field, which are congruent to 1 modulo every single prime in Tk, right? So for example, if T contains 2 primes of different residual characteristic, that implies right away that there are no roots of unity in the top field, which are congruent to 1 modulo every single prime in Tk. And I want T and S not to touch one another, so their intersection is empty. And now, to this setup, I can associate some arithmetic objects, okay? The first one is a generalized ideal class group. It's the so-called S comma T ideal class group. So these are fractional ideals in the ring of S integers of the top field, which are co-prime to T, mod out by principal fractional ideals in this ring, which have a generator which is congruent to 1 modulo every single prime W in Tk. Now, this is an ideal class group. It's finite, and it has a class field theoretical interpretation, if you want. I mean, it corresponds via the Artin reciprocity map to the maximal abelian extension of capital K, which is unramified outside T. It's completely split at S, and it's almost tamely ramified at T, okay? You know, there is a group of units floating about, and those are the so-called S comma T units. And what are these? So these are elements X in Henri's GM of OK comma S. So those are S units in your top field, right? Which have the additional property that are congruent to 1 modulo every single prime W in Tk. In order to simplify things, later on I'll drop S and T from the notation because S and T will be fixed throughout the talk, okay? So U sub S comma T will become U, A sub S comma T will become A. And then X sub S is simply the set of Sk divisors of degree 0 in capital K. So those are formal sums in the primes in Sk with coefficients in Z such that the sum of the coefficients is 0. Okay? Again, this depends on S. It doesn't depend on T, but I'll even drop S from the notation, so this will be referred to as X in what follows, just for simplicity. Please note that all these objects, A, U, and X, come endowed with a Z bracket G module structure. G acts on them. They are, therefore, Z bracket G modules. Okay? And now, one little remark. You see, this X that you see over there it's very easy to understand. I mean, just divisors of degree 0 over sk. But U itself is very difficult to understand as a Z bracket G module, that is. Well, even as a Z module, I know it's finitely generated via Dirichlet's theorem, and I know its rank over Z. But I have no idea how to produce generators. Okay? But its structure as a Z bracket G module is much more difficult to understand. Okay? Its cohomology groups over G are very difficult to understand. Nevertheless, if you tensor these two objects, U and X is this easy to understand object and U is the hard to understand object. If you tensor them with R, they become isomorphic, canonically isomorphic as R bracket G modules. And the isomorphism is given by this regulator map, which depends on S. So it's minus the sum for all W in Sk of the logarithm of a normalized absolute value associated to W, evaluated at U, times W for every single U in capital U, and then you extend it by R linearity. And what happens is you get an R bracket G isomorphism. And this is the so-called R bracket G equivariant, or the G equivariant regulator map. And now one observation that you can make, you know, an elementary application of representation theory of finite groups will tell you, well, since these two modules, RU and Rx are in fact defined over Q, so in other words, they are obtained from Q bracket G modules by tensoring with R. What is? It's the real numbers. It's boldface R, yeah, as opposed to this capital R, which denotes the G equivariant regulator. Okay? So what I was trying to say is that since these two representations are in fact defined over Q, and they are isomorphic over R, they are in fact isomorphic over Q as well. So there should be a Q bracket G module isomorphism between QU and QX. And there is one, but that's not a canonical one. Okay? So it's not as easy to understand. But we know theoretically that such a thing exists. However, if you view these as integral representations, as Z bracket G modules, the two are by no means isomorphic. And we understand X. It's very easy to understand as a Z bracket G module. But we have no idea about the Z bracket G module structure of U itself. Well, let's see. So here is where the L functions come into the game. So I'm going to describe the analytic side of the story now. So I'm going to talk about the G equivariant L function associated to this picture. First, I'll take any character, complex valued character of G. Please recall that G is abelian, so characters are homomorphisms from G to C cross. And I associate to this guy an analytic object, the so-called S comma T L function associated to chi. And for the real part of the complex number little s greater than 1, this is defined as an infinite product, okay? So the infinite part is over here in the second product. So that's the product for all the primes V not belonging to S of 1 minus chi evaluated at the Frobenius sigma V associated to V in this extension times the norm of V to the negative S. As you know, the norm of V is just the cardinality of the residue field associated to V to the power negative 1. Now that's an infinite product, but on the real part of S greater than 1, this is absolutely and uniformly convergent on compact subsets. So it gives rise to an analytic function, and now you multiply that by a finite product, automatically analytic, over all the primes V in T of 1 minus chi evaluated at the Frobenius associated to V times the norm of V to the power 1 minus S. Okay? So on the real part of S greater than 1, this gives rise to a holomorphic function for every single chi. And now, miraculously, all these holomorphic functions can be extended actually to holomorphic functions on the entire complex plane. Okay? Now, it's not a good idea if you want to study Z bracket G module structures. It's not a good idea to study these functions independently. It's a better idea to put them together into a so-called G equivariant L function, and this is going to be denoted here by theta. And that's a function defined on C with values in the group ring C bracket G with coefficients in C. How do I obtain this theta? Well, I sum over all the characters chi, and then I have the L function associated to chi times the idempotent in the group ring C bracket G associated to chi inverse. Okay? So you should think of this as a holomorphic function on the complex plane, but taking values inside C bracket G, where C bracket G should be thought of as finitely many copies of C. Okay? Cardinality of G, many copies of C. You know, what we are interested in, and this is where the special values come into the game, we are interested in the leading term of the Taylor expansion of this function at s equals 0. So I'm looking at all these individual L functions, I'm expanding them at s equals 0, and I'm taking the first non-vanishing coefficient for each of them. I denote that by L star of chi comma 0. Sum them up, multiply them by the appropriate idempotents, and I get the leading term of this G equivariant L function at s equals 0, and I denote that by theta star of 0. A priori, this is an element in C bracket G cross. These are the invertible elements in C bracket G. But in fact, it turns out that it's an element in R bracket G cross. Okay? Yes, please. Yeah, the order of vanishing of these L functions could vary with chi. For each of them, I'm really taking the leading term in the Taylor expansion. So I'm dealing with derivatives of different orders here. The order depends on chi. Good point. Okie dokie. So now the game I'm going to play is this. What I want is to establish a link or a bridge between this G equivariant invariant of analytic nature, which is this theta star of 0, and the various arithmetic invariants that I described before, units, XS, A, and so forth. But I want to understand their Z bracket G module structure, not only their Z module structure. Okay? You know, just to give you an idea of what that link might look like, or why there should be such a link, let me just show you just one facet of this link. So please recall, let me just align this properly. Sorry about that. Okay. So please recall that we have these isomorphisms between Ru and Rx, and that's given by this R bracket G equivariant regulator. Well, the first hint that there might be a link between the L functions described here and the arithmetic lurking in the background of this picture is given by the second half of this slide. The second half of this slide simply tells you that if you want to understand the order of vanishing, these orders of vanishing that were mentioned by Henri Darmon in the previous question, the order of vanishing of the individual L functions at s equals 0. So what is the order of vanishing at s equals 0 of the L function associated to chi? Well, it turns out that that's the dimension of the C vector space obtained by taking the chi eigenspace of Cu. But since Cu is isomorphic to Cx as C bracket G modules, that's also the dimension over C of the chi eigenspace of Cx. And since we understand Cx very well, I can compute this dimension. So what is it? Well, it turns out that if the character is different from the identity, then this is simply the number of primes V in S, such that if you restrict the character chi to their decomposition groups, then you get the trivial character. And in the situation where chi is the trivial character, then this is just the cardinality of S minus 1. So this is giving you a precise description of the order of vanishing of these L functions. Now, since we understand these orders of vanishing, why don't we group these L functions by orders of vanishing? And that is the same thing as grouping the idempotents corresponding to the characters out of which these L functions are constructed by order of vanishing. So this is what I'm going to do next. So for every single n in Z, I'm going to denote by En the idempotent in C bracket G for the moment, which is obtained by simply adding up all the idempotents E sub chi such that the L function associated to chi has order of vanishing precisely n. Now, this is an idempotent in C bracket G a priori, but in fact, due to this description over here of the order of vanishing, you can see right away that this idempotent is in fact in Q bracket G, because the order of vanishing of the L function associated to chi is equal to the order of vanishing of the L function associated to any conjugate of chi under the action of the absolute Galois group of Q. You can see that from this description, right? So these are idempotents in Q bracket G. Sorry about that. This leads to a decomposition of Q bracket G into some eigenspaces with respect to these orders of vanishing. So the eigenspace corresponding to order of vanishing n is En Q bracket G. And according to what I'm saying here, the dimension over En Q bracket G of the corresponding eigenspace associated to Qu is precisely n if the idempotent is different from 0. Okay? All right. So clearly, at least the order of vanishing of the L functions is explained in terms of these arithmetic objects, U and X, that I just mentioned. But much more is going on here. So you will see in just a moment what I mean. Well, in order to tell you what's going on, really, I should tell you a little bit about determinants. Okay? So this is part 1 of my chat about determinants. There will be a slightly more sophisticated treatment of determinants coming up later. So what is this? So R is a commutative Noetherian reduced ring, and I would like you to think of R as being either Z bracket G or Q bracket G or R bracket G. Okay? These are good examples. And in fact, the talk will reduce to those examples as we approach the end. But for the moment, R is just a commutative Noetherian reduced ring, and P is a finitely generated projective R modules. Yeah? And to this projective module, you can associate a rank function, which is a continuous function on the spectrum of R with values in Z. The spectrum of R is viewed here with the Zariski topology. Z is viewed with the discrete topology. And what is this rank function? Well, it associates to every single prime ideal in the spectrum the dimension of the localization of the projective module of that ideal over the localization of the ring. As you know, projective modules over local rings are free. And since this is a finitely generated guy, it's going to be free of finite rank. So I have that. Turns out that this is continuous in the two topologies that I mentioned, and therefore it's locally constant, and therefore I can split R. So this is where the Noetherianness of R comes into the game. I can split R into a finite direct sum of rings, Ri, such that if you restrict the rank function associated to P to the spectrum, to the spectrum of Ri for every single I, then you get a constant function equal to Ni. So this is like a stratification of the spectrum with respect to this function. I'm doing Morse theory on the spectrum, if you want, for those of you who are familiar with topology. All right, so, but this is very simple. So then, once I have this stratification, I can consider the determinant over R of this projective module, which is this direct sum over all these i's of the R'th exterior power over capital Ri of P tensor over R with Ri. So at each I take the top exterior power. This means that at each I get a rank 1 projective module over Ri. So this means that overall, when I take the direct sum, I get a rank 1 projective module over capital R, and that's the determinant. This is also called an invertible module, right? Because if you hit it with its dual, then the tensor product of the two, it's isomorphic canonically via the evaluation map with R itself. That's why it's called invertible. All right. This is functorial. This construction is functorial in some sense. It's weakly functorial, in fact. In the following sense, well, if you have an isomorphism of R modules, P and Q, called the isomorphism F, then you can associate to that the determinant of F in the obvious manner. Well, if they are isomorphic, then their rank functions are the same. So the top powers will be the same. So you get this determinant of F, which establishes an isomorphism between the determinants of the two modules. All right? An example, which is relevant to our situation here. So please recall that I have this decomposition of QU into eigenspaces, and the dimension of each eigenspace, En QU, is precisely n. So if you think of the ring R as being Q bracket G, 1 second. So R is Q bracket G. Well, Q bracket G is a sum of fields, so everybody is projective over that. In particular, QU is projective, so it makes sense to take the determinant. Well, the determinant is precisely that. It's the nth, the sum over all n, the nth exterior power over En Q bracket G of En QU. There was a question back there.
Can you explain one more time what you mean by that notation with the exterior and the Ri on the bottom and the little Ri on the top?
Yeah, so that's the Rith exterior power of the capital Ri module P tensor over R with Ri. Yeah? That's what happens. And then I'm taking the direct sum over all i's. Yeah, that's what happens. All right, so that's an example. And then, well, here is how L functions come into the game. So, now I'm tensoring everything with capital R. So I can take the determinant over R bracket G of Ru. R bracket G is another sum of fields, so everybody is projective over that, so I can take this determinant. You know, it turns out that there is a canonical regulator map, which is denoted here by script R. This is this black script R over here. Taking your determinant into R bracket G. Okay? How is this constructed? Well, first of all, I have my regulator map Rs, which is an isomorphism between Ru and Rx. Ru and Rx are projective modules. I take the determinants, I take the determinant of the regulator, and I get this isomorphism over here, canonically. And then it turns out that I can establish a canonical isomorphism between the determinant of Rx and R bracket G, but I have to tell you, so I won't describe this in detail. You know this part, you don't know this part. But what's the beauty about the second part is that, in fact, it's defined over Q bracket G. So you see, Rx is Qx tensored over R bracket G with Q bracket G. Over Q bracket G, Qx is a projective module. I can take the determinant of that. I establish an isomorphism between the determinant of that and Q bracket G, and then I tensor it with R. This is how this second green arrow shows up. And then the black arrow, this script R, is just the composition of the two green arrows. Okay? You know, the blue module here is well understood, R bracket G, I understand that. And the thing is that the L functions give me a Q bracket G, a natural Q bracket G module structure on R bracket G. How is that? Well, I simply take the free rank 1 Q bracket G submodule of R bracket G generated by this theta star, by this special value of my G equivariant L function. Okay? And now I pull it back via this regulator, script R. And now the question is, what do I get inside this determinant? And this is the first big conjecture that was formulated in the 1970s by Harold Stark. And Stark simply conjectured that, in fact, what I get is the natural Q bracket G submodule of this determinant. In other words, is the determinant over Q bracket G of QU, the units. This conjecture is far from being proved. I mean, even in the abelian case, we don't know how to prove it. But let's assume that we did. Okay? Well, if we assume that, then we can go further. You see, inside this Q bracket G theta star, I have a natural Z bracket G free rank 1 module, the one generated over Z bracket G by this special value of theta, this theta star of 0. You know, the big question is, what is the pre-image via this regulator map of this Z bracket G theta star inside the determinant over R bracket G of RU? Well, if Stark is correct, then this pre-image should be a Z bracket G submodule of this guy. Okay? Free rank 1 Z bracket G submodule of that guy. This pre-image will be denoted by L. One of the most important unsolved problems in number theory today is trying to understand this lattice L, this Z bracket, free Z bracket G submodule of this R bracket G space over here. If we understand this, then a lot of unsolved problems will just end up by being solved right away. One example is Hilbert's 12th problem. Okay? Explicit construction of abelian extensions of global fields. We have no idea how to do that, but if we understand this lattice, then we can. Okay? So,
And so the determinant of ZQ doesn't work?
the determinant?
Of ZQ?
Oh, not at all. So that would be the guess, right? It should be the... Well, first of all, why is that the wrong guess? Well, U itself is not a projective Z bracket G module. So the determinant over Z bracket G of U doesn't make sense. You will see that U has non-trivial cohomology over G. Therefore, it's not projective.
However, U is torsion-free, as everybody.
It is torsion-free, but over Z is projective. Over Z bracket G, it isn't. This is what I was telling you. We understand the Z module structures here. But that doesn't mean that we have any clue about the Z bracket G module structures. So let's even suppose that U is projective over Z bracket G. That happens by accident, very rarely, but it happens. I could show you some examples tonight if you want. Is the determinant over Z bracket G of U equal to this lattice? Not at all, almost never. This is a very subtle invariant, and we have no idea what it is at this point, not even conjecturally. Okay? So what does L do? I'm just going to try to explain to you how we are trying to study this lattice L. What does L do, in fact? Well, what it does is it captures the difference between this well-understood Z bracket G module, which is X. These are the divisors of degree 0 supported by S. And this not so very well understood module over Z bracket G, which is the group of S units, S comma T units. And then, so this is what L is supposed to do, is to capture this difference between these two Z bracket G module structures. And then the regulator R is supposed to tell you, well, the difference is in fact hidden in this special value of your G equivariant L function. So really the regulator links the difference to the special value, theta star of 0. Okay? You know, let me show you some attempts that people over the years have made to understand this lattice L. Okay? So among these people, well, I should mention Stark, who started looking at this integral version of the problem in 1980, and then Rubin continued, and then I did some work in the late 1990s. So what we did is this. Well, we decided, well, studying the lattice L is hopeless. So why don't we break up the lattice L into n eigenspaces with respect to n equals the order of vanishing of the various L functions, right? So this means what? When, on this side, on the right-hand side of this diagram, this means that I can split up this module, this Z bracket G free module, rank 1, into various eigenspaces. Yeah? But be very careful, Z bracket G theta star is not the direct sum of the eigenspaces, it's just inside the direct sum of the eigenspaces. Right? because Z bracket G itself is not the direct sum of En Z bracket G. If you tensor with Q, then you get equality, but if you stay over Z, then this is bad. And then, rather than looking at the pullback of Z bracket G theta star, just look at the pullback of each of these eigenspaces. What do you get? Well, you get a direct sum of the various eigenspaces corresponding to the idempotence En associated to the lattice L, so this ENL. And then Stark, Rubin, and myself tried to just study some of these eigenspaces, give you a description of some of these eigenspaces, ENL. Okay? And let me show you some samples of what we came up with. So the point I'm trying to make here, and this will be quite relevant from the examples I'm going to discuss, is that this lattice L, even if you split it up into eigenspaces, even if you look at parts of it, pieces of it, these eigenspaces, it packs up a staggering amount of mathematics. Okay. Most of the fundamental theorems in number theory are in fact encoded in this lattice, as you will see in just a moment. So for example, let's look at the simplest possible example where capital K is equal to little k. That is, the Galois group is the trivial group. Then Dirichlet's class number formula. It's equivalent up to a sign, up to a plus or minus, to saying that the lattice is nothing else but the order of this ideal class group A that I mentioned earlier times the exterior power over Z of U mod out its torsion. So this is U tilde, so you mod out U by the roots of unity. But in this situation, the roots of unity are not there. So U tilde is in fact U. The exterior power is the top exterior power, is the cardinality of S minus 1. That's the rank of U over Z. Dirichlet's class number formula up to a sign is really a statement about this lattice, the equality between this lattice and that. If you think about it, that's what it is. And now, let me make some simplifying assumptions. So go from K equal to little k to a general extension, capital K over little k. And let's assume that S contains R primes which split completely in capital K over little k, and that the cardinality of S is greater than or equal to R plus 1. And let ER be the idempotent corresponding to order of vanishing R L function. So this, it turns out that this is the minimal order of vanishing. Yeah. So what happens in the case R equals 0, so if you look at the E0 eigenspace associated to L, then the various conjectures that I am listing in red here on that side, some of them are theorems, some of them are conjectures, are in fact statements about this E0L. So the first one is a theorem. That's the Dulin-Ribet theorem that was proved in 1979. It was proved, in fact, by Weil over function fields. So the 1979 theorem is for number fields, and that's the difficult part here. And that simply says that the value at 0 of this theta belongs to Z bracket G. That is nothing else but saying that the E0 eigenspace of L is inside Z bracket G. It's equivalent to that. Okay? So the lattice really, if you understand the lattice, then this theorem would be a consequence of that. Just this piece, the E0 piece of the lattice, would imply this theorem. Now, there are refinements of this theorem, and the refinements are conjectural in nature. So, for example, there is this Brumer-Stark conjecture, which simply says that this theta of 0 belongs to the annihilator of the ideal class group. That's nothing else but saying that E0L is inside the annihilator over Z bracket G of the ideal class group. So it's a statement about the lattice. There is a further refinement due to Gross, which simply says, well, this theta of 0 is in fact in an intersection of products of relative augmentation ideals associated to the various decomposition groups associated to the primes V in capital S. Well, that's again a statement about the E0 piece of this lattice. So if you knew the lattice, then you would be able probably to see that E0L is inside this intersection, and that would imply Gross's conjecture. This is in fact a refinement of Gross's conjecture due to John Tate. All right. So now, So what happens if R is equal to 1? So this is for R equals 0. I was looking at the 0 eigenspace of the lattice. But how about R equals 1? So there is a famous conjecture due to Harold Stark here, saying that the E1 eigenspace is inside, in fact, the group of units. So this is Stark's conjecture stated in 1980. Okay? Well, we have very little evidence for this conjecture, but let me tell you what we know. So we know how to prove the conjecture, for example, in this situation where the base field is Q, and if the top field is a real cyclotomic field, Q of zeta m, zeta m is as usual the primitive m order root of unity, then it turns out that the lattice, in fact, E1L, is generated over E1 z bracket g by a remarkable element, by a cyclotomic unit. Okay? So if you knew the lattice, then you would know E1 of L, and then you would know these special units, the cyclotomic units, which happen to generate most of the maximal abelian extension of Q. So this should give you a hint of how Hilbert's 12th problem might be hidden, the solution might be hidden in this lattice. Now, if the characteristic of K is P greater than 0, so we are talking function fields, again, we know how to prove Stark's conjecture for R equals 1. And it turns out that this E1 eigenspace of the lattice is generated by a torsion point of a rank 1 Drinfeld module. These ones also generate the maximal abelian extension of the base field. This is work of Drinfeld and Hayes, 1980s. Okay? Now, if K, little k, is a quadratic imaginary field, then again we know how to prove Stark's conjecture, and E1 times the lattice is generated by an elliptic unit. That is a special value of a modular unit at quadratic imaginary quantities in the upper half plane. Yeah. Again, this is clearly linked to explicit abelian class field theory over a quadratic imaginary field. And now, recently, there is a promising development in the situation where the base field is a real quadratic field, where we don't know how to prove Stark's conjecture. And recent work of Darmon and Dasgupta has produced a conjectural p-adic construction of this epsilon, which will generate E1L over Z bracket G. For the moment, these are just p-adic formulas. One would hope that one can come up with global formulas for this. And conjecturally, this is what they are predicting. So I'm really looking forward to talking to Henri during my stay here about this new development, which I find very promising. Okay? So that's R equals 1. What happens for R greater than or equal to 1? Well, for R greater than or equal to 1, Carl Rubin and I in the 1990s developed some conjectures regarding this lattice ER lambda. And we conjectured that ER lambda is generated over the corresponding ring, that is ER z bracket G, by an element epsilon, which a priori belongs to this Q bracket G vector space, but it satisfies a remarkable property. If you hit it with R minus 1 elements in the dual over Z bracket G of the group of units, viewed as a Z bracket G module, then you end up with an actual unit. And this special unit will be the analog of elliptic units, torsion points of rank 1 Drinfeld modules, or cyclotomic units, or perhaps the Darmon-Dasgupta constructions of these special units in the case where the base field is a real quadratic field. So if such a unit exists, then we can prove at this point that, that these units give rise to general Euler systems, and as a consequence, they lead to refined class number formulas, a la Grach conjectures, for example, and they give a solution to Hilbert's 12th problem in full generality. So all this is just in an eigenspace of this lattice, the eigenspace corresponding to the idempotent of minimal order of vanishing, this ER. Okay? And now, recently, I formulated some conjectures regarding the other eigenspaces, so En lambda for every single n, and there is some evidence for those. I'm not working under the hypothesis that S contains R primes which split completely anymore. I'm working in full generality. But proving these conjectures seems to be quite hard, even if the base field is Q itself, for example. So if you are dealing with higher order of vanishing L functions, things get very complicated. In any instance, even if we prove these conjectures, all we are going to understand are these pieces, E and L, and as I said before, L is not, in fact, the direct sum of the eigenspaces. It just sits inside the direct sum of the eigenspaces. And actually, what we want is L itself, not the eigenspaces. So we want L. Okay? Now, the theory that we've developed so far doesn't seem to lead to L itself. It seems to lead to this direct sum of the various eigenspaces, which is, an easier to understand Z bracket G module. Okay? So how do we understand L? Well, the ideas behind understanding L itself come from work of Burns and Flock that I mentioned earlier. And Burns and Flock built upon work done by many other people. And I said Bloch, Kato, Fontaine, and Perrin-Riou. And here is the idea. So the idea is this. Well, please recall that L is supposed to capture the difference in Z bracket G module structure between X, which I understand, and U, which I don't. Now, why don't we do this? How about trying to measure the difference via a complex of Z bracket G modules, a cochain complex of Z bracket G modules, and then try to understand the lattice in terms of this complex. So forget the two objects, X and U, just measure the difference between them via a complex of Z bracket G modules, and then try to explain the lattice in terms of this complex. Now, this is the general idea behind going from the category of Z bracket G modules to its derived category. Replace the objects by the projective resolutions, for example, of the objects. So what Burns and Floch are proposing when they are stating this equivariant Tamagawa number conjecture in this case is, well, forget Z bracket G modules. Move into the derived category and do your work there. And then, if you're lucky, you can come back into the category of Z bracket G modules. So let me explain how this is done. Well, for that, I'll have to do some more determinant theory. So this is the second half of my chat about determinants. So again, please recall that I have a ring which is reduced, commutative, and Noetherian. This is the ring R, and I'll denote by Q of R the total ring of fractions. Since R is reduced, this Q of R is going to be a sum of fields. And I'll denote by A Q of R algebra, arbitrary for the moment, but what you have to have in mind is Z bracket G, Q bracket G, and R bracket G. So Z bracket G is your ring R, Q bracket G is its total ring of fractions, and the Q bracket G algebra that I have in mind is really R bracket G. Okay? And now, let's suppose that I have an R module M, and then I call it perfect if its projective dimension over R is less than infinity. So it is of finite projective dimension over R. That's what perfect R modules are. Now, an example, please recall, I mean, you saw some Galois cohomology last week. Over the ring Z bracket G, a module is perfect if and only if it is cohomologically trivial, which means that if you compute its state cohomology groups, HI hat, associated to every single subgroup delta of G, then you get 0. That's what cohomologically trivial means. So determining whether a Z bracket G module is perfect, in other words, it has finite projective dimension over Z bracket G, amounts really to computing these cohomology groups. Yeah? So it's perfect even if and only if all these cohomology groups are 0. And now we are moving into the world of cochain complexes. So when do I call a complex perfect? So this is a complex of R modules. Well, I call it perfect if it is bounded. That is, it's 0 to the left and to the, if you go far into the left and far into the right. And it's quasi-isomorphic to a bounded complex of projective R modules. Two complexes are quasi-isomorphic if there is a morphism between them, which leads to isomorphisms at the level of cohomology. That's, yeah? So I call a complex perfect if it is quasi-isomorphic to a bounded complex of projective R modules. And now a little remark here. The object M is perfect, the module M is perfect, if and only if the associated complex is perfect. And this associated complex has M at level 0 and 0 outside. That's very easy to see. And now, if you have a bunch, finitely many perfect modules, and you put them together into a complex, necessarily bounded, then that is perfect. But not vice versa. So if you have a perfect complex, the components of the complex are not necessarily perfect modules. Okay? Okay. So we have that. And then what I would like to do is extend the notion of a determinant to the world of perfect complexes. Okay? So by the way, all these remarks you can take as exercises. They are easy exercises. If you have questions about them, you can ask me. They are good exercises in homological algebra and the cohomology of groups that you saw last week. Okay? So from now on, by a complex, I mean a bounded complex of finitely generated R modules. And then a complex M is called cohomologically perfect if its cohomology groups, viewed as R modules, are perfect. That is, they have finite projective dimension over R. Now, it turns out that if a complex is cohomologically perfect, then it is perfect, but not vice versa. Here is another exercise for you. Okay? And now, let's suppose that you have a cohomologically, so let's suppose that you compute the cohomology groups of a complex. And you put together the odd ones, the odd indexed ones, into an R module of this type. So that will be denoted by H odd of M dot. So that's the direct sum of all the odd cohomology. And the even ones you put together into H even of M dot. Okay? You know, so the cohomology is divided into two R modules. Okay? The odd one and the even one. And now, given a complex M dot of R modules and the Q of R algebra, A, if you have an isomorphism between the odd cohomology of the complex tensored with A and the even cohomology of the complex tensored with A, then you call that isomorphism an A trivialization of your complex. Okay? So this can happen. So for example, HO over R may not be isomorphic to H even over R, but if you tensor it with a big enough ring, then you may get an isomorphism. If you get such an isomorphism, then you call that a trivialization over this big ring of the original complex. I'll show you examples in just a moment, examples which come from number theory, actually. So here is what happens with these determinants. I foresee that I'll go over time by about 5 minutes, so I ask for your forgiveness here. And I thank you in advance for it. Here is how you do it. So you have the projective R modules, finitely generated projective R modules, with isomorphisms, endowed with isomorphisms. That's a category. I showed you that you have a determinant functor from that category into the category of invertible R modules, that is rank 1 projective R modules, with respect to isomorphisms. This is the determinant that I showed you first, okay, when we first started talking about determinants today. But now what happens is this. You can embed the category of projective R modules with isomorphisms into the category of perfect complexes of R modules with respect to isomorphisms. Yeah? So any module gives rise to a complex by simply sticking that module into level 0 and filling up the complex with zeros outside. That's a perfect complex. Okay? Now the question is, can you close this diagram with a functor, this capital det determinant functor, which takes every perfect complex into an invertible R module, canonically and functorially? And the answer to that question is yes. And you can do it uniquely up to a unique isomorphism if you impose upon this functor some additional properties. This is a big theorem. It's a theorem that was proved by Mumford and Knudsen in 1976, and they were heavily building upon earlier work of Grothendieck. Actually, Grothendieck suggested this problem to them. Okay? So this is the so-called Mumford-Knudsen determinant functor, and what it does, it takes a perfect complex of R modules, and it makes it canonically into an invertible R module, into a projective R module of rank 1. Okay? Now, I won't be able to define this functor for you. It's complicated. I can give you references, but I should give you some examples. So if your complex is made up of projective modules, then the determinant, the Mumford-Knudsen determinant, is just the tensor product of alternating determinants, to the powers plus or minus 1 of the components. So it's the determinant of pi, which we know what it means. This is the classical determinant of a projective module, to the power -1 to the I plus 1. Well, if the power is plus 1, then you know what that means. If the power is -1, then what that means is you take the dual of that module. The dual of an invertible module is another invertible module. So you take the tensor product of those over R. And that's the determinant of your complex. And now it turns out that if your complex is cohomologically perfect, in other words, its cohomology groups are individually R modules of finite projective dimension, then there is a canonical isomorphism between the determinant of the complex and the determinant of the odd part of the cohomology, tensored with the determinant of the even part of the cohomology. Sorry, there is a -1 missing. So the even part shows up at the -1 power here. Okay? All right. So this is a lot of nonsense here. Abstract nonsense, but it will make a lot of sense to you if you see an application to number theory, and that's coming in just a moment. Okay? All right. So a little more abstract nonsense. So what happens if you have a complex, perfect complex of R modules endowed with an A trivialization? A, I remind you, is just an algebra over Q of R. Then what happens is, well, there is a commutative diagram which looks like this, which takes you canonically from the determinant of your complex into A itself injectively, and the image of this map, okay, gives you a canonical invertible R submodule of this algebra A. Okay? So I would like to go over this diagram, but it's quite complicated and I'm running out of time. So what you have to keep in mind is this. If I give you a perfect complex of R modules, okay, with an A trivialization, then automatically you can associate to it an invariant, which is an invertible R submodule of this algebra A. And this is denoted, this invariant is denoted by capital C associated to the complex C dot and associated to the trivialization T sub A over the algebra A. So this is a canonical construction. I'm not making any choices here. And that is because this Mumford-Knudsen determinant functor is unique up to a unique isomorphism. Okay? So now let's see. I mean, do I have such things coming out of my number theoretic setup? Well, I do. And I do due to work done by Tate in 1966. So in other words, what I want is this. Well, I want to understand the difference in Z bracket G module structure between X and U. But I want to understand this difference in terms of perfect Z bracket G module complexes. Okay? And there is such a complex. So here is Tate's theorem. I'm going to work under the simplifying assumption that the ideal class group A is equal to 0. So if that's satisfied, you can always do that by increasing the set S. If you throw enough primes in S, then the S ideal class group is going to be 0. So let's suppose that that's so. Then there exists a canonical class tau in x2 over z bracket g of x by u with a representative of this type. So this is an exact sequence of z bracket g modules starting with u and ending with x, and with two terms in the middle, q and p, which have the property that the projective dimension of these two elements over z bracket g is less than or equal to 1. Well, automatically, this leads to a perfect complex. The perfect complex is the complex q goes into p. Q is at level -1, p is at level 0, and I have 0 outside. Yeah? The projective dimension of q is less than or equal to 1. The projective dimension of p is less than or equal to 1, so they are perfect modules. The rest is 0, so this is a perfect complex of z bracket g modules. Okay? What is the cohomology of this complex? Well, the cohomology of this complex, the odd cohomology is just H1, which is my U, the guy that I want to understand. And the even cohomology is my X, the guy that I know. This is my friend. This is the guy that I want to understand in terms of X. But I have the complex. I have the Tate complex that links the two. So now I'm going to apply the Mumford-Knudsen construction to this Tate complex. But in order to be able to apply the Mumford-Knudsen construction, I would have to have a trivialization. Do I have one? Of course I do. We started this lecture with such a trivialization. So what are the rings? Well, you have Z bracket G, you have Q bracket G, that's the ring of fractions, and you have the algebra R bracket G. If you tensor the two cohomology groups, the odd and the even cohomology groups with R, then you get Ru and Rx. The trivialization is given by this regulator that I started my lecture with. That's an isomorphism. Okay? So now, to this trivialization and to Tate's complex, you associate this invariant, Xi, associated to Tate's complex, and the trivialization given by this regulator. What is that? Well, that's an invertible Z bracket G submodule of R bracket G. Okay? Conjecture. This is the equivariant Tamagawa number conjecture for this motive. If there are some of you who know about motives, so the motive involved is H0 of spec of K, and it has coefficients in Z bracket G, but you can just forget whatever I said. Okay? So the equivariant Tamagawa number conjecture of Burns and Flach in this context simply says that this, I have 2 more minutes to go. So the equivariant Tamagawa number conjecture turns out to imply all the conjectures that Stark, Rubin, and myself made regarding these eigenspaces. And this is not surprising. The ETNC captures L. It should capture the eigenspaces. But we could have been wrong in conjecturing whatever we've conjectured about the eigenspaces. Well, this is a good sign for us. ETNC also implies whatever we conjectured. And if you tensor ETNC with Q, then you capture Stark's original 1970s conjecture over Q. This is very easy to see. This is the conjecture that I stated towards the beginning of the lecture. And now I should end with a couple of theorems, if I still have them here. Yeah, it does. Yes, the equivariant Tamagawa number conjecture explains what L is. That would be technical, okay? So I am not going to explain what L is, but you can capture L, this equality. Yeah? I can explain that, for example, tonight or in the upcoming days. But in any instance, so you have to take my word for it, this actually captures L, not only the eigenspaces. Okay? And now, a few theorems. So the equivariant Tamagawa number conjecture is true if the base field is Q. So this is a big result due to Burns and Greiter. They proved it up to a power of 2. This is the meaning of this tensorization with Z adjoint 1/2. And Flach eliminated this doubt at 2. So he proved it if you tensor it with Z2. So that led to a full proof of the equivariant Tamagawa number conjecture for K equals Q. Now, the equivariant Tamagawa number conjecture in characteristic P is known up to a power of P. So we don't know it at P. And this is a result of Burns. And now there are questions. I mean, are the conjectures of Rubin and myself true in characteristic P at P, the P part of these conjectures? We know that the equivariant Tamagawa number conjecture would imply those, but we don't know how to prove the equivariant Tamagawa number conjecture at P. Well, luckily, we can prove the Rubin-Popescu conjectures at P in characteristic P. So that's a theorem that Kiseng Tang and myself have proved recently. I should end here, except for the fact that I should say that, as I said at the beginning, this can be done for very general motives. So what this conjecture, or what this equivariant Tamagawa number conjecture does for a more general motive is it relates the motivic cohomology, which in this case is represented by the units, to the Deligne cohomology of the motive, which in this case is represented by Rx, yeah, divisors of degree 0 supported by S. And you will see that if the motive is an elliptic curve, then the equivariant Tamagawa number conjecture, in its simplest case, the situation where capital K is equal to little k, is nothing else but the Birch and Swinnerton-Dyer conjecture. So in some sense, from the equivariant Tamagawa number conjecture point of view, the Birch-Swinnerton-Dyer conjecture is somewhere at the bottom of the food chain. You can make it into a very sophisticated Z-bracket G equivariant statement, but that is not to say that we have any idea of how to prove this Z-bracket G equivariant statement. Okay? Thanks.